Hello. In this video, I'm going to go over section 13.4, Green's theorem. But before I go over the theorem, I want to remind you of some notation and even a theorem. So if I'm in R2, then my vector field has components P and Q. These are functions of X and Y. Another way of writing this is saying that F, it's equal to P in the direction of I plus Q in the direction of J. Now, if I have a curve in my vector field, let's say this is C, if I have this curve, then I'm assuming that I can write it in terms of t and only t, meaning that the position at any time t, it's given by this parameterization that depends on t and only t. The last thing I want to remind you of is that the line integral of f along C, it's given by this, which we saw is work. So it's just the force that the vector field has to apply on the curve to, say, move a particle from point A to point B, okay? So this is the actual notation of my line integral, but we saw that if you want to actually calculate this, we use the fact that r is equal to r of t, therefore dr dt, it's equal to r prime of t, therefore my differential dr is just r prime of t dt, okay? So this is where this comes from. So we saw that, on top of that, we saw that if this vector field has a property, then there's no need to calculate the line integral like this. So let me remind you, that is from section 13.2. Section 13.2, we saw that if my vector field has no circulation, then that means that it is conservative. F is conservative. The definition of the field being conservative means that then it is the gradient of a function, which is called the potential function. It's like you're able to find the antiderivative, if you will. And then a way of testing this is by showing that if you take the partial of p respect to y, you get the same as the partial of q with respect to x, okay? So if my vector field satisfies this, then the line integral f dot dr, it's equal to my function, the potential function evaluated at the ending point, minus the potential function evaluated at the starting point. And this is a big deal. Once you find, it's just a fundamental theorem of calculus, right? But it's called the fundamental theorem of line integrals, which tells you that your line integral, it's path independent. Path independent. So it doesn't matter if I'm going from A to B. It doesn't matter if this is A and this is B. If I go like this, or I go like this, or I go like this, it doesn't, or I go like that. Doesn't matter how I get to I. Doesn't matter how I get from one point to the next one. Now, this one assumes that in order for this term to work, I need no circulation. So what happens if there is circulation? That's what we're doing now. This is section 13.4, which means that I got this wrong, and this should be 13.3. Okay, so 13.4, it's when we're going to talk about Green's theorem, and this is good for when there is circulation, meaning dp dy, it's not equal to dq dx. So let me go over the theorem. Green's theorem. So of course I had to have some Green. It's called Green's theorem because it was proved by, is it George Green? So that's why it has his last name. Anyways, so let's see. It says, let C be a positively oriented, piecewise smooth, simple, closed curve in the plane, and let D be a region bounded by C if P and Q have continuous partial derivatives on an open region that contains D. Then I promise you in a minute, I'll tell you what everything means, okay? But long story short, under all of these circumstances, then we see that my line integral, which we saw, this is the same as the integral over C of f dot dr. So under these circumstances, it's also equal to the double integral over d of the circulation dq dx minus dp dy dA. So we're taking this from a line integral to an area integral, okay? Now, before I give you the intuition, because I'm not going to prove it, before I give you the intuition, I want to say a couple of more things and then define each of these things, okay? So, another notation for positively oriented boundary curve D is this. So, what I'm saying is, if this is, let me make it more interesting. So, this said here that it's a curve in the plane and D is the region bounded by C. So C is the boundary and D is what's inside, right? So this will be, in other words, this will be like the line integral and this is an area integral. So the one that goes along C, the one that is inside D. But another way of calling C is just saying the boundary of D, okay? Perfect. We just like the way I think about this notation, it's like this is the derivative. So it's like I'm going down 1 degree. Okay. Another notation for this is saying instead of writing over C, we just put a little circle there because it means it's a closed curve. Okay. They all mean the same. All right. Now, let me go over each of these things. First of all, if I have meaning that the orientation is positive, it means counterclockwise. That's all it means. It means counterclockwise. So maybe I should take this with me. So that means that if I'm here, then counterclockwise means it's moving in this direction. Okay? Because it has to do with this integral has to do with circulation, so that is actually very, very important. Okay? Perfect. Now, piecewise defined or piecewise smooth means that you could have something like this, which even though it has those little corners, if you look at it piece by piece, then it's still defined. And then you have to make sure that it has the correct orientation. So let's see. It has to be like this. Okay. And then let's say if I say that this is C1, and this is C2, and this is C3, and then the whole thing, the combination of the three lines is C, then I can say that C, it's actually just C1 union C2 union C3, meaning that the integral over C is just the integral over C1 plus the integral over C2 plus the integral over C3, okay? Now, another condition is that it has to be simple, so no sub-intersections. So by that we mean what you think it means, okay? So it can have, let me stick to pink. I'm liking the pink. So it can't have intersections. So if you cannot have something like this or something, I don't know, right? So if it has an intersection, then we don't want it. And then it has to be closed. So the starting point and the end point have to be the same, which, I mean, what else, right? If it starts here, it does whatever, and then it has to end at the same point, okay? Perfection. Now, let me give you the physical interpretation of this, which is like the closest we're going to get to a proof. So maybe I'll take this one with me. So I take this one with me. So this is now my curve. This is the curve. It's a closed curve. So this is C, and whatever is inside, I'm going to call D. So D is the region bounded by C, okay? And I have, this is important, right? It has some circulation. It has some orientation. So imagine now, let me finish this real quick. Imagine now, I take my region and now I do what we always do. I split it into a bunch of little sub areas, little sub squares, okay? So I do that. And then imagine now, I look at the circulation inside my region, okay? So imagine there's like some fluid here. Imagine it could be anything. So if I focus on one of them, let's say here, there is some circulation. It has to be, everything has to be counterclockwise. So if I have here and I look at the circulation here, it's going to go in this direction as well, right? There is circulation in my vector field. So if I look at the circulation inside my vector field, it has to go in that direction, okay? So what the theorem tells me is that the circulation around my curve, like in the exterior, by definition, this is the integral over c of f dot dr. This is the circulation on the boundary is the same as if I add all the little circulations, okay? And now it's going to be in terms of A. So if I take this one, the circulation here, it's just the curl. Well, now I'm in 2D, but it's the same formula. So it will be, so if I'm here, the circulation just at this spot, it's given by dq dx minus dp dy. That's the circulation at one of the points. So in theory, what we're doing is we're adding all of them, and then I have to multiply by the area, which is dA. Well, it's not dA, it's going to be delta A. And then I can take it to the continuum. So then that's how I end up having that. This is equal to now the double integral over my region of the little circulations, dq, it's dq dy minus dp dx and then dA, okay? So maybe let me tell you what this is. So this is a circulation on the boundary, and this is not the correct shade. That's a circulation on the boundary, and then this is the circulation, the total rotation, the sum of all circulations inside the domain, in the domain, okay? And this is just the total rotation. I'm gonna say rotation, okay? So the way I think about this is, it's like, imagine you have one of those like robots, like the vacuums, and it's, if it doesn't work right, then it'll be rotating the same direction, right? So eventually everything that you have here, it'll end up at the boundary because it cannot leave the boundary. So you're rotating, everything ends up at the boundary, okay? Perfection. Let's do an example. What I'm going to do with my first example is that I'm going to solve it both ways. I'm going to solve it by just using the definition of the line integral and then by using the theorem, okay? Because that's the important thing. If I have any problem that I have, if I have my line integral, if I want the line integral, and I know the parameterization R, I can compute it by just doing f of r of t dotted with r prime of t dt, okay? But the theorems make your life easier, okay? So first, I'm going to do it directly. By that, I mean I have to parameterize my curve and then compute the line integral of each of the lines here, okay? So let me show you what I mean. Let's first understand what's happening. I want to evaluate this integral, and then I have that C is the triangular curve consisting of the line segments. So let me draw that. So this is 0, 0, and then I go 1, 0. So this is 1, 0, and then it goes to from 1, 0 to 0, 1. Okay, so it goes from 0, 0 to 1, 0, and then from 1, 0 to 0, 1, and this is 0, 1, and it goes in the direction that it should be going, and then it goes from 0, 1 to 0, 0, so it goes in this direction, okay? And then I'm going to say that this is C1, C2, and C3, and I have to parameterize each of them. So let's parameterize them. Okay, so let's see, C1, you can just do it using like the standard parameterization. This is a line, so this is the equation of a line. If you don't want to think too much, you just do it. You just go, okay, I'm starting at 0, 0, okay? And then I'm moving in the direction of 1, 0. So I'm moving in this direction. So my direction vector will be 1 minus 0, 0 minus 0. So I get that this is 1, 0. That means that r it's equal to, what is this? T 0. That means that, and d is equal, it's in between 0 and 1 always. That means that x it's equal to t, therefore dx is equal to dt, and y it's equal to 0, so dy it's equal to 0, right? Okay, perfect. And then along C2, r it's equal to, let's see, I'm starting at 1, 0, so my r naught is 1, 0 plus t, and then my direction vector goes from 1, 0 to 0, 1, so it's in that direction. So I need the difference. So this is 0 minus 1, I get negative 1, 1 minus 0, I get 1. So r, it's now 1 minus t and then t. That means that x is equal to 1 minus t, y it's equal to t, dx is just negative dt, and dy it's equal to dt. I have one more parameterization along C3. So along C3, I have that r. Again, I'm starting at 0, 1. I'm moving in the direction of 0, 0. So that means that the change in x is 0. The change in y is negative 1. That means that my line is the line 0 plus t, 0, and then 1 plus negative t. So 1 minus t. And then again, t, I stopped writing that, but we see that for my parameterization, t is always in between 0 and 1. So here I have that x, it's equal to 0. Therefore, dx is equal to 0. Y it's equal to 1 minus t. Therefore, dy it's equal to negative dt. That is it for the parameterization. Now I'm ready to find my line integral. Let me write it here so I can see it. So it's the integral over c of x to the fourth dx plus xy dy, okay? If you want to like make your life easier, like don't forget what's happening, then you can recall that this is just the integral over c1 of x to the fourth dx plus xy dy, and you're going to use the parameterization for C1. By that I mean you're going to use the x definition, the y definition, the dx, the dy along C1. And then once you move and you're finding the same integral but along C2, then everything changes because we have a different parameterization, okay? And this is C3, x to the fourth dx plus xy dy. All right, so this is equal to, and now I'm going to again use my parameterization. So along C1, x is t. So this is the integral from 0 to 1. Everything depends on t now. 0 to 1. X is t, so this is t to the fourth. Dx is equal to dt. So we have dt plus x times y. X is t, y is 0, so I get 0 times dy, which is also 0. So I'm done with the first parameterization. I'm done with setting up my integral in terms of t. Now along C2, I have that x is equal to 1 minus t. So this is the integral from 0 to 1 of x, which is 1 minus t to the fourth. And then dx is negative dt. So negative dt plus x times y, which is 1 minus t times t. And then dy, and dy it's equal to dt. Perfect. And then I'm almost done. Third one, 0 to 1. X to the fourth, it's equal to 0 to the fourth. Dx is equal to 0. And then I do x times y, which is 0 times 0. So this one, there's no contribution for this last one, okay? So this is plus 0, okay? So let me simplify this so that I can find my antiderivatives, okay? So this is 0 to 1, t to the fourth. I'm going to combine everything into one integral plus 1 minus t to the fourth, which with that negative I'm going to put it in the front. So minus 1 minus t to the fourth, that looks like a 9. So to the fourth. And then I have plus. Now here I have 1 minus t times t, so I get t minus t squared dt. Perfection. And then what else do I have? I'm ready to do this. This is t to the fifth divided by 5. And then the antiderivative of this, since this is a line, I don't need to use u sub. So this is just minus 1 minus t to the fifth divided by 5 divided by the derivative of 1 minus t, which is negative t, not negative t, negative 1. So I'm going to say times negative 1. Make a little note, this is the derivative with respect to t of 1 minus t, okay? And then I have plus t cubed divided by 3, plus t squared divided by 2 minus t cubed divided by 3. From 0 to 1, so this is equal to 1 over 5. And then here I have, if I plug in 1, that goes away. And then I have plus 1/2 minus 1/3. Perfect. And then I have, if I plug in 0, then this goes away. And then I get that this is, hold on, let me just do it. So this is that minus 0, and then this is minus 1 over 5, right? Because this one and this one is positive. So I have minus, so I have plus 1 over 5, and then 0 and 0, okay? Plus. Okay, so then when I simplify this, I get that the 1 over 5 goes away with the 1 over 5, and my final answer, I'm almost done, it's equal to 1/2 plus, not plus, but minus 1/3, which is equal to common denominator 6. 6 divided by 2 is 3, minus 2, 1 over 6. This is just me doing this, doing it directly, but I want to apply the Green's theorem, okay? So let me now, first of all, double check that I can actually apply Green's theorem. So 2, Green's theorem. So it's the integral over c of x to the fourth dx plus xy dy. I have the same exact curve, copy paste. Okay, so this is what I want, where this is c, and I want to use Green's theorem. Should I be using green? I should. I'm like wasting the opportunity of using green for Green's theorem. So Green's theorem. Okay. Green's theorem. Perfection. All right. So let's see. Let's just remind you what's happening. We're solving this. We're evaluating this integral. This is c. The orientation still matters. I no longer need to turn this into 3 curves. This is 1 curve. And this is d, whatever it's inside, okay? So I have to figure that out. Not a problem for us. First thing I want to remind you that x to the fourth will be p, xy is q. I have to do dq dx, dp dy. dq dx is equal to just y. dp dy, it's equal to 0. Okay? And then you go, well, since dq dx is not equal to dp dy, we're good to go, okay? And these are continuous, and this is simply connected, and everything is satisfied, okay? Since the circulation is not 0, and everything else, let me say all the conditions are satisfied, and all the conditions are satisfied, Green's theorem applies. Okay, so let's see. So Green's theorem says that then this is going to be equal to, the double integral over d of dq dx minus dp dy dA, okay? Perfect. So what is my integration region? What is this? Well, we know x goes from 0 to 1, not a problem. So here easily we see that x goes from 0 to 1. This is like a type 1 integral. And then I need the equation of this line, not a problem, it's just a line. So it goes from 1, 0 to 0, 1. I just need to connect that, okay? So I can say that this is, the slope is the change in y over change in x, so I get -1. And then this is just y equal to, what is this? This is that, and then I put my slope, so -1 times x minus y, which is 1, okay? So I'm using this point to find the equation. I finally get that y is equal to 1 minus x, okay? So you go -x plus 1. Perfect. So x goes from, that means that this is x goes from 0 to 1, and then y goes from, right? Y goes from 0 to this line. So this is what's happening here, right? It's top, bottom. So y goes from 0 to 1 minus x, and then dq dx dp dy, well, we have it here. Dq dx is y, and then dp dy is just 0. And then I have dA, which is just dy dx. That's it. And this has to be equal to 1 over 6, because math never lies. But I feel it's much easier. So let's see. This is equal to the integral from 0 to 1. This is my iterated integral. I take the antiderivative of y respect to y. I get y squared divided by 2. My bounds are from 0 to 1 minus x. And then I do dx. So this is the integral from 0 to 1. Plug in the bounds. I get 1 minus y squared divided by 2 minus, plug in 0, you get 0 dx. And then again, since the inner function is just a line, I don't need to use u sub. I also don't want to expand this, but you could if you wanted to. This is equal to 1 minus x cubed divided by 3 times the 2 that we had to begin with. So this is 2 times 3. And then you have to divide by the derivative of the line, which is -1. So that's my denominator there. And then I have to go from 0 to 1. Let me simplify this. So I get that this is 1 minus x cubed divided by -6 from 0 to 1. When x is equal to 1, I get 1 minus 1, 0, minus when x is equal to 0, you get -1 over 6, which is 1 over 6. Ooh, math never lies. We got the right answer. Perfect. What else do we have? Now we have evaluate this integral where c is the circle x squared plus y squared equal to 9, okay? So, perfect. Let me start by just saying, okay, fine. This, just because of the way it's written, the moment I see that I'm dealing with the closed curve, I go, smells like Green's theorem. So this is P and this is Q. So before I even try to understand my region, let me see if this has no circulation, okay? So I go here, dq dy, it's equal to the derivative of this respect to y, which it looks super hard, but this is, wait, whoops, x, which it looks super hard, but this goes away and you get 7. And then dp dy, pretty much the same idea. Here, oh, where is it? Here, that goes away and I get 3, okay? So they're not the same. So dq dy not equal to, why I keep saying dy? dq dx not equal to dp dy. I do it a lot, but then my brain goes, no, it has to be like cross derive, okay? So, and they're continuous, and this is my region, which is simply connected, it's positively oriented, is smooth, the derivative, everything looks good for Green's theorem, okay? So here we go. Let's see. Let me understand my region. So my region is a circle of radius 3, center at 0, 0. So this is -3, and this is 3, and this is 3, and this is -3. And this is C, right? The equal sign, the boundary C. And then what's inside, it's D, okay? So let's see. So this is D. And then we can say this, it satisfies all the conditions. We see that it is, so C is positive oriented, right? This is the way a circle goes. So that's good. We have that. Let me just go like that. Wonderful. We have that. It is simply connected, right? There's like no self-intersections. We also see that it is smooth. Come on, cannot be better, which means that the partial derivatives are continuous, which we already know. So this is looking good. Everything looks good, okay? So let's see. So according to the theorem, then we have that the integral that we have over here is equal to the double integral over d of dq dx minus dp dy dA. Now, let's understand this. I'm integrating over the region bounded by a circle, so I can use polar coordinates. So using polar coordinates, I can describe D saying that, okay, x is equal to r cosine theta, y is equal to r sine theta, x squared plus y squared is equal to r squared. We know that dA is equal to r dr d theta, and r goes from 0 to 3. R goes from 0 to 3, and theta goes from 0 to 2 pi. Okay? Now, in this case in particular, the beauty of this is when we did dq, dx, dp, dy, we got constant. So we didn't have to plug these values for x and y. So that made our life a lot easier. But long story short, my double integral I'm writing now in terms of polar coordinates. So r goes from 0 to 3, theta goes from 0 to 2 pi, dq dx is equal to 7, dp dy is equal to 3, and dA, my differential, now in polar coordinates, don't forget the extra r. So this is 7 minus 3, r dr d theta. All right, so this is just the integral from 0 to 3, the integral 0 to 2 pi for r dr d theta. And you know by now that I like to write this as the product of two integrals so that I don't have to do the iteration of integrals. So r goes from 0 to 3. I can take the 4r with me. So this is dr times the integral from 0 to 2 pi d theta. There's like a 1 here. When I solve this integral, I get 4r squared divided by 2 from 0 to 3. And then I get theta from 0 to 2 pi. I'm almost done. This is 2r squared from 0 to 3. And this is just theta evaluated at 2 pi. I get 2 pi. And then I'm here, and I get that this is 2 times 3 squared minus 0 times 2 pi. My final answer is 9 times 2. What is that? 18 times 2, 36 pi. Perfection. All right. What else do I have? I have one more example. Yeah. Okay, so it says a fluid flow in the plane with velocity given by this, velocity field given by this. Let's see, be a positively oriented boundary on the region R enclosed by the parabola and the x-axis. Compute the work done by the fluid in moving a particle once around the curve C in the counterclockwise direction, that is, evaluate the work integral. And this is overkill. It's either or, okay? I either put this notation or I put the C. So I went with the closed curve here. Perfection. Same idea. First of all, one more time, whenever you see that it's a closed curve, Green's theorem. Smells like Green's theorem, but we have to check. Okay, let's make sure that it actually, the main thing to prove is that it does not have zero circulation. Okay, so let's see. Let me see. 1, d, so this is p and this is q, so dq dx and dp dy. So q is equal to x squared. I take the derivative with respect to x, I get 2x. P is equal to negative y. I take the derivative with respect to y, I get negative 1. Okay? And then you go, well, 2x is not equal to negative 1. So 2x not equal to negative 1. That is good. Okay. On top of that, we have everything that we need. Okay? The problem is telling me that C is positively oriented. The problem is telling me that I'm moving counterclockwise, which is the same thing. Why is this? Okay, whatever. And then this is the region that we are bound in. Okay, so let's understand that. So let me just say here, like C satisfies all the conditions for Green's theorem. All the conditions for Green's theorem. So let's understand the region right here, right? So my region is, it says C is enclosing this parabola and the x-axis. Okay, so this is the graph of my parabola. It is a parabola that it opens down. Okay, so it's something like this, and then this is 4, right? When x equal to 0, you get 4, and then when this is equal to 0, you get x equals plus minus 2. So then x goes from negative 2 to 2, negative 2 to 2. And then this is again positively oriented. I don't know why I'm writing it backwards, but this is what it means. And this, the region, this would be my region, right? This is C. That's C, the boundary C. Let me maybe make it blue. So this is C. And then the interior, right? The region that it's being bounded by that is D. Let me change the color. I really like the peach and then I don't like it anymore. All right, here we go. To perfection, D. So the theorem tells me then that for my work, it's equal to the integral over the closed curve f dot dr. Do I need to parameterize this? No, because I know that I can use Green's theorem. So this is equal to the double integral over the region that the curve is bounding. And then I have dq dx minus dp dy and then dA. Okay, perfection. Now, what is my region? So according to this, and we know how to integrate over a two-dimensional domain, right? We did this before. We see that x goes from negative 2 to 2. So x, it's in between negative 2 and 2. So we did this when we talked about double integrals. Now, y goes from 0 to the curve. But we already know what this curve is. So y goes from 0, right? 0 to the curve. Okay, so one more time. This is y equals 0, and this will be y equals 4 minus x squared. Okay, so those are my y bounds. Let me maybe keep them red so you see where they come from. So let's set this up. This is equal to x, since this is the constant one, this is the first one, so this is negative 2 to 2. And then y depends on x, so this is a type 1 integral. It goes from 0 to 4 minus x squared. And then my integrand is just here, the rotation, which is dq dx, so 2x, minus dp dy, which is negative 1, so plus 1. So minus negative 1, so plus 1. And then I have to do dy first, because these are the y bounds, and then I do dx. Okay? So here I have to iterate my integrals. There's no other way to do this. So let me start by, I have my negative 2 to 2. I'm going to find this integral with respect to y. So I get 2xy plus y, and y goes from 0 to 4 minus x squared. And once I'm done with that inner integral, I do dx. So this is equal to negative 2, 2, 2. Replace y with 4 minus x squared. So I get 2 times x, 4 minus x squared plus 4 minus x squared. And then replace y with 0. So you get y, keep moving. And then this is 0. And then dx. I'm going to simplify the integrand. So this is negative 2, 2, 2. And I multiply this times 4. So I get 2 times 4, I get 8x minus 2x times negative x squared. I get minus 2x cubed plus 4 minus x squared dx. I'm going to do something I really like, which is using the fact that I'm integrating from negative 2 to 2. I'm integrating over a symmetric interval. So I'm going to write this by splitting it into even and odd. So this is the same as the integral from negative 2 to 2, 8x minus 2x cubed dx plus the integral from negative 2 to 2, 4 minus x squared dx. Now we know that, let me make everything smaller so I can fit it here. Now we know that that first integral, 8x and 2x cubed, they're both odd. So since these two are odd, since this is an odd function, then the integral over negative 2 to 2 is just equal to 0. Okay, so this is just 0. And then since this is even, then I don't have to do the integral from negative 2 to 2. I can just say this is 2 times the integral from 0 to 2, 4 minus x squared dx, which is equal to 2 times 4x minus x cubed divided by 3 from 0 to 2, which is equal to, I'm down here now, 2 times, if I plug in 2 here, I get 8 minus 8 divided by 3, and then plug in 0, you get 0. I'm almost done. This is 2 times. Common denominator 3. 3 times 8 is 24. 24 minus 8 is equal to 16. So my final answer is 16 times 2. You get 32 divided by 3. Perfection. Hope you liked it. This is a beautiful, beautiful theorem, okay? Hope everything made sense. Bye-bye.